Hi, let's continue on with KMT. This time, we will try to derive several equations. Okay, now before we begin deriving, let me first lay out to you what model are we using. Here we have a molecule in a box, okay, a single molecule, okay, moving or colliding with the wall at this direction and bouncing off like this. So this is the path taken by the molecule. Now on your right side here is the model we're in, which we will begin to use. Here is the gas molecule, okay, and here is the wall of the rectangular vessel. Now this molecule here is moving at a specific direction, at this direction. And so its momentum is its mass times its velocity. Okay, now this velocity here has different component. We have here the x component and the y component. Before bouncing off, this is its components. Now after bouncing off, the direction is changed. However, the magnitude of the velocity is unchanged because earlier we mentioned that collision of the gas molecule with the wall is elastic. And so it's the same length of the arrow, but the component's direction is changed, particularly that of the x component. So you can see here, the x component is reversed. However, the y component of the velocity is unchanged. Okay. Therefore, if we write the change in momentum of the molecule in that direction, what we'll be having is the final momentum, which is negative mvx minus the initial, which is mvx. That gives us negative 2 mvx, the change in momentum of the molecule. Now that momentum is transferred to the wall after collision, and so the momentum change of the wall has similar magnitude but opposite sign. That gives us 2 mvx. Now, the time taken by this gas molecule here to move from here to here and back here is what we call delta t. This is the time elapsed between collisions of the same molecule in the same wall, and that is twice the length, okay, the length of the rectangular box divided by the velocity at which that gas is moving at that direction. Now we have to divide this momentum with this time, and you will see the reason why later. Delta t, that gives us 2 mvx divided by 2L divided by Vx. This simplifies into mvx squared divided by L. Alright, now we have this ratio over here. And now we continue on with, okay, by defining the force. The force exerted by that molecule is equal to mass times acceleration. The mass of that molecule and the acceleration at which it's moving. Now we know that acceleration is the change in velocity with time, right? And this expression here is what? This is the change in momentum. Okay? Change in momentum over change in time, which is similar to this previous expression over here. And so that this left hand side is equated to what we have derived earlier, mvx squared over L. This now represents the force exerted by one molecule of gas on the wall when it collides on the wall. Now, in a gas sample, okay, it contains several number of molecules inside. There are millions of, or more than millions of gas molecules present in for example 1 mole of gas in a sample of gas. And so we have to calculate the total force exerted by that sample. And so what we do is we multiply this mvx squared with the total number of molecules inside, and this would represent to us the force, the total force exerted by that sample of gas. Now, earlier we mentioned in the assumption that the velocity at which the gas molecules are moving are not the same. Each of the gas molecules are moving at different speed, and so we cannot express this velocity as one velocity alone, so we have to put bar there. This bar here represents, let me just fix that bar. This bar here represents the average, that the velocity we're talking about is the average velocity, and that average velocity is what we call the mean square speed. Mean square speed or mean square velocity, and it's simply the average of all the square of that velocity and that component x n square. Okay, so that's the mean square velocity. Now this is the total force exerted by the gas sample. Alright, now from here on we'll continue by calculating for the pressure. Now pressure is force over area. Now this big F here, force, is nmvx squared over L, and multiply that by the area. And now what do we have here? What we have here is volume. Length times area, okay, we're still referring to this box, is the volume of that box. And so this simplifies into P equal to nmvx squared bar, don't forget the bar there, divided by the volume. Alright, now you start to see the Boyle's law in this equation, isn't it? Pressure there and volume there. If I bring pressure here, it becomes PV. Alright, but we don't stop here. We first look at this again, the velocity here, x component. Again, going back to the assumption, we mentioned that gas molecules move at different direction, isn't it? And so we have to take care of that. We cannot just express the velocity as the x component. So we have to use the resultant velocity or resultant speed for this. So what we do is we express Vx squared in terms of the u squared, the mean square speed. And u squared is the sum of the average square of all the component, Vz squared. Okay, because one velocity can have 3 components, corresponding to the 3 axes in a Cartesian plane. And so the u squared here, or the speed, is equal to the sum of these 3. Now all of these 3 has the same magnitude, okay, they have the same length. And so what we do is we simplify them into adding them equally, like this. All of them can be expressed as one variable here, Vx, and so that gives us Vx squared equal to 1/3 u squared. It's that simple. And we use this and substitute it here to give us P, let's bring volume there now, nm u squared bar. Okay. Now, oh sorry, we have to, don't forget 1/3 there. Alright, now what we have is the equation, okay, which represents our first goal. The goal we mentioned earlier that tells us that the Boyle's law is related to the microscopic movement of molecules, because in this equation this tells us that the pressure is directly proportional to the speed at which the gas molecules are moving. The faster they move, the higher the pressure they exert, and the more number of molecules present, the higher the pressure they also exert. Okay. Now in the next slide we will be deriving temperature. Now